Hello and welcome to another day of Advent of Code. We are here for day 17, which is a problem that's very similar to day 11, so I'll try and remember to link day 11 below. We're going to actually solve it in almost exactly the same way. So let's jump into it. Okay, so the input to the puzzle today is a map of cubes in a plane, and the cubes will be activated if they are an octothorpe. And if we look at part 1, you can see this is what our input might look like, and so this has these particular things activated. And a note here that I mentioned that it's a map of cubes in a plane and not in a, not in a two-dimensional thing. So we're given an input of a plane, but it will extend upward and downwards. And so this is a 3D Conway's Game of Life problem. Day 11 was kind of a 2D Game of Life problem, but a little bit different. And the way that I decided to represent my input for this problem is as a set of coordinates. So you can see this is my type here, because we really only care about the activated ones. In day 11's problem, it was a little bit more complicated. We had to care about both activated, activated or filled, empty, and aisle. We had 3 different types, but now we only have 2 different types, so we can represent the presence or absence just based on this set here. So if it's in this set, that means it's activated. If it's not in this set, that means it's not activated. This also, greatly limits the amount of data that we're going to store as we compute our algorithm. Unlike the other videos, I'm actually going to combine the parsing and the computation into the same function. This is just because it made more sense that way. The parsing for part 2 is going to be a little bit different. But anyway, the 3D Game of Life problem says that if three activated neighbors, it becomes activated. Exactly 3. So not 3 or more, exactly 3. And actually, was it 3 or more? Now I'm second guessing myself. Day 17, part 1. Exactly 3. Okay. Spoilers, that's how we're going to implement it. And if it was previously activated, it can be either 2 or 3 active neighbors. There's actually a shortcut that I didn't implement in my problem. We'll see if it works today. I think it does. Oh, I forgot to put in the samples here. Day 17, part 1. So for part 1, we expect 112. Expect 112. And part 2, we expect 848. So I'll just write that down for now. Usually I do that before, but I forgot to do it this time. Anyway, let's do the parsing first. So the parsing here, we're going to have a set of 3D coordinates. So we're going to assume that everything in that plane starts at 0, 0z. We can actually adjust that however we want. And I'm going to represent this as z, y, x, which is kind of backwards that you might represent it, but that's, it doesn't really matter where the coordinates are as long as you're consistent throughout your problem. And so this is a series of lines of characters. So for line in s dot split lines. And then we actually want to get to the y coordinate here. And then for x comma c in enumerate line, we are going to append to our set a coordinate here. So set s dot ret dot append dot add. Our z coordinate is going to be 0, our y coordinate is going to be y, and our x coordinate is going to be this. But we're only going to do that if c is equal to an octothorpe. Now, if you watched my comprehensions video, anytime you see a series of just simple fors and ifs, we can represent this as a comprehension. And so we can just do this in one big old line by taking this here, reordering it up here, removing the add, and then indenting all of these properly and removing their colons. And so this is a set which is a double for loop that filters the characters that have to be octothorpes here. And so if we run this now, Python 3 part1.py, and I invalid syntax. Oh. What is this? Activated. Forgot to put the parameter there. And you can see that we get a set. It's not ordered, so let's actually sort this just so it's a little bit easier to see. And so we see 0, 0, 1, which is this one here. The y is 0 and the x is 1. 0, 1, 2, that's this one here. And then we see, 2, 0, 2, 1, and 2, 2 for this final row here. So that's the parsing. The neat thing is when we take this to 4 dimensions, all we're going to have to do is do this here. So it's going to be really easy to augment this solution for part 2. All right, so let's do our 3D game of life problem. The first thing that I noted here is that we're doing 6 rounds. So what I did here is for underscore in range 6. That way we're going to, just continually, we're going to run this for 6 iterations. My initial thought when I saw this problem is like, oh no, what if they extend this to a bigger number? But fortunately that didn't happen. I think there's probably a generalized solution for this, but I didn't bother to look at it. And at the end, we want to return the number of activated things. Unfortunately for us, that's just len activated. We're going to continually overwrite this activated set as we do our iteration here. Okay, I'm going to use the algorithm that I used for day 11. So I'm going to mark around each of the activated things and increment a counter. And that way these 2 rules will be a lot easier to implement. So we're going to do marked equals collections.counter. And this is going to be, we don't really see it here, but it's a counter of tuple int. We also need to do import collections. And I did a video on counters, so I will try and remember to link that in the description as well. So the keys to our counter are going to be coordinates, and they're going to be, how many neighbors are activated, essentially. And so what we're going to do here is we're going to loop over z, y, x in activated. So we're going to look at our previous state here. And then we need to modify -1 and +1 for each of these. And the way I did this was just kind of a silly bunch of nested for loops. There's probably a more clever solution, but I think this is readable enough. For zi in -1, 0, 1, and for yi in that, and for xi in that. So looping over all of those different coordinates. And of course we want to filter out when all 3 of them are 0. So if zi equals yi equals xi equals 0, we're going to skip that one, so we can just do a continue here. And otherwise, we're going to mark each of those values, each of these coordinates with its offset. So we're going to do marked z plus zi, y plus yi, and x plus xi. Oh, another thing that I forgot to mention. The input on the Advent of Code problem for this day is particularly confusing. So if we look at day 17 here, they give a sample input after cycle 1, but they fail to mention that this is not on the same coordinate plane as part 1 was. Mostly if you look at this spot here, it has 5 around it, so it should not become activated, but it looks like it becomes activated here. And what's actually happened is it's shifted in some direction. So I mostly just ignored the sample input. I found that it was not helpful for actually solving the problem. But anyway, so we want to do marked plus equals 1. That will take our offsets here and mark everything around each of the marked things. And once we've built up this marked list here, we can now apply the new rules here. So we want a new activated set. So new activated equals a set. And we have 2 rules here. If it's 3 activated, it becomes activated. So let's loop over everything in our counter. And if it has a value of 3, then we will put it into new activated. So for kv in marked.items, if v is equal to 3, so if it's exactly 3 neighbors that are activated, then new activated.add k. And so that, that adds that there. We also need to take all of our previously activated things and check if they had 2 or 3 activated neighbors. And so we can do for k in activated. If new activated k is in 2 or 3, then wait. If activated, if marked. I have the wrong variable here. Then new activated dot add k. note K, I didn't bother to expand it here. This is going to be one of these 3 tuples here. The same for this one here. I could have put XYZ, but we'll actually see that causes us to write more code for part 2. I believe there's a shortcut here where you can just say equals equals 2, because we've already checked all the ones that are exactly 3. We'll try that when we run this. I didn't actually try it in my solution though. And we get 5. We expected to get 112, so clearly we have done something wrong. Oh, 5 is the original value. So we forgot to reassign activated. Activated equals new activated. And the reason that I made a separate value here is we need to, cross-reference back to the original activated here. We could actually shortcut this. I'm gonna try and shortcut this in a second if this still works. Okay, so 112 is what we expect. Let's try doing equals equals 2. That also works. And I think what we can do here is we can actually take this first part here and do that first and do activated equals, and we can turn this into a comprehension. We can do K, for K and activated if marked K is equal to 2. And so that'll get us our first set of activated things, and then we can ignore this here and just do activated.add, and then we don't need a separate state variable. So a little bit of reordering there. It does give us the same value, and then we don't have to maintain as much state. We're just immediately replacing it here. But anyway, that's part 1. We're actually not going to modify this code, so I don't need to show you the more interesting or the less interesting version of this, but we're going to leave that there. Part 2 is very, very similar to part 1, except we extend this problem to 4 dimensions instead of 3 dimensions. And fortunately for us, we're just going to copy part 1 to part 2.py. And the modification here is very, very straightforward. So instead of having tuple int int int, let's replace that. Tuple int int int. And again, like this might be a case where using a type alias is helpful. So let's actually, well, we'll just do the dumb replacement. So we're gonna go from 3 ints to 4 ints here. So we're gonna replace all those. And so that works all fine and dandy. But we need to extend our coordinate system to do that. So let's adjust our parsing now, and we add a W dimension. So then you have W, X, Y, Z. But we're actually doing W, Z, Y, X. It doesn't actually matter, but that's how I thought about this. And then the other thing we have to do here is we need to extend this to loop over the proper coordinate here. And we need to add one more loop for the W axis. So for WI in -1, 0, 1, we need to indent all this. And we need to change this to also check for WI equal to all the others in 0. And we need to add WI, or W plus WI into here. And that's all we need to do to modify for part 2. So it's really just taking the first problem and extending it ever so slightly by adding this dimension. And let's see, the expected for part 2 is 848. And we do get 848. Now note that this is kind of slow. But if we look at our algorithmic efficiency, it's actually not bad from an algorithmic efficiency standpoint. Now note, algorithmic efficiency doesn't actually give you a good look into how this actually executes, but let's look at it. Okay, so this loop is a constant amount of work, so we can kind of ignore that. We don't really know how activated grows over time, but you can probably imagine that, at worst it multiplies itself like by some constant factor. So like you have 2 things, then you have 10 things, and then you have some order of magnitude larger. And so this is probably about linear, if I had to guess. These loops here make it look like the the algorithmic efficiency explodes out. But you'll note here that these are all over a constant factor. So these, even though it's 3 times 3 times 3 times 3, this 81 is constant over the number here. So even though k is large, the O of n is still, or the big O is still somewhere near ON. It's probably more like ON squared if I had to guess, but it's hard to know based on how this algorithm expands outwards. But you can think of it as ON. At least that's what I'm gonna say. But anyway, this is day 17. Hopefully this was helpful, and I'll see you for the next day.